Close your eyes and drift away into a quiet question. What if time isn't as steady as you think? What if seconds stretch and contract, clocks tick slower or faster, and the universe itself bends space and time into strange, beautiful shapes? Tonight, we wander through relativity, softly, slowly, to let your mind drift as the world of physics becomes your lullaby. When Albert Einstein was a young man, he would often sit alone and let his mind wander in ways that seemed unusual to others. He wasn't the kind of scientist who spent all his time hunched over laboratory equipment. Instead, he liked to imagine simple things and let those simple things unfold into bigger questions. One of his favorite ideas was to picture what it would be like to chase after a beam of light. He would close his eyes and wonder, if I could travel alongside that light beam, moving just as fast as it does, what would I see? At the time, this was not the kind of question most physicists asked. Light seemed to be just another wave, like sound or water. But sound and water waves always depended on something else, air, water, or some other medium, to carry them along. People thought light must work the same way. They even imagined an invisible substance called the ether, which was supposed to fill all of space and provide a medium for light to travel through. Yet no one could find any proof that this ether really existed. Einstein thought deeply about this. He imagined himself moving faster and faster until he reached the speed of light. If light were just a wave in some material, then perhaps he could catch up to it and see a frozen wave, standing still in space. But experiments had shown that this never happens. Light never stands still. No matter how fast you move, you will always measure light moving at the same speed away from you. This was confusing because, in everyday life, speeds add and subtract. If you run toward a car that's driving away from you, you reduce the distance faster than if you stand still. But with light, the usual rules break down. He thought about the famous Michelson-Morley experiment, which had tried to detect the ether by measuring tiny differences in the speed of light as Earth moved through space. The experiment found no difference at all. This puzzled scientists, because if Earth were moving through the ether, then the speed of light should vary depending on Earth's motion. But it didn't. Light always traveled at the same speed, no matter what. So Einstein sat with this strange fact. Light doesn't care about the speed of its source, and it doesn't care about the speed of the observer. This seemed impossible under the rules of classical physics. It meant that either something was deeply wrong with our understanding of light, or something even stranger was true. Our entire idea of time and space might need to change. He kept thinking about what it meant to chase a beam of light. He imagined an observer standing still, watching a clock tick, and another observer moving very fast, also watching that same clock. If light always travels at the same speed, then time must adjust itself to keep that speed constant. This was not a comfortable idea. It meant that time was not an absolute river flowing the same for everyone, everywhere. Instead, it could stretch or shrink depending on how fast you moved. To test this, he turned to thought experiments, or Gedanken experiments, as he called them in German. One famous image is of a train moving through a lightning storm. Imagine a train car moving quickly along the tracks. Two bolts of lightning strike the front and the back of the car at the same time, at least according to an observer standing on the platform. But what about a passenger riding inside the train? For the passenger, the flashes don't reach them at the same instant. The train's motion means they are moving toward one flash and away from the other. The speed of light is the same for both flashes, so the one they move toward reaches them sooner. This simple idea shows that what looks simultaneous to one person might not be simultaneous to another. Einstein realized that if events can look different to different observers, then our common sense idea of time as something fixed and universal must be flawed. To save the constant speed of light, you have to allow time and space to become flexible. Distances and durations are no longer the same for everyone. They bend and shift, depending on how you're moving. This was the seed of special relativity, which Einstein published in 1905, a year he would later call his miracle year. He wasn't yet a famous professor. He worked at a patent office in Bern, Switzerland, reading other people's inventions all day and scribbling his own equations during quiet moments. He had time to think because he didn't have to spend hours in a lab. He had the freedom to drift through ideas like a mind riding on a beam of light. Special relativity is built on just two postulates. First, the laws of physics are the same for all observers moving at constant speeds, what physicists call inertial frames. Second, the speed of light in a vacuum is always the same for every observer, no matter how fast that observer is moving. These two statements, though they sound simple, lead to results that are anything but ordinary. One result is time dilation. If you move very quickly, time slows down for you compared to someone standing still. This isn't just theoretical. Experiments with high-speed particles, atomic clocks on airplanes, and satellites all show that it's real. Another result is length contraction. An object moving near light speed shrinks along the direction of motion, at least from the perspective of someone watching it fly by. All of these strange effects come directly from the fact that the speed of light doesn't change. It's the universe's ultimate speed limit. Nothing can move faster than light, because to do so would require an infinite amount of energy. As you push an object to higher and higher speeds, its energy increases without bound, making it impossible to reach or exceed light speed. When Einstein first proposed this idea, it wasn't immediately accepted. It was so different from what people were used to. Newton's laws had ruled physics for centuries, and they said that time and space were fixed backdrops. Suddenly, a young patent clerk was suggesting that these backdrops bend and flex like fabric. But over time, experiments confirmed his predictions again and again. One of Einstein's gifts was that he didn't see thought experiments as mere daydreams. To him, they were tools for exploring the hidden rules of nature. He knew that our everyday senses can be misleading when we deal with things moving close to light speed. The trains and light beams that filled his imagination became guides into a world that defied common sense. Perhaps the most beautiful part of his insight was that he found order in what looked like chaos. The constant speed of light wasn't an odd glitch. It was a clue that the universe was far stranger and more elegant than people realized. By giving up the idea of absolute time and space, Einstein uncovered deeper symmetries that connect everything. The simplicity of imagining a single light beam changed the world. It showed that sometimes the most powerful scientific tools are not heavy machinery or complex experiments, but quiet moments when a mind is free to ask, "What if?" This way of thinking didn't stop at special relativity. Later, Einstein wondered what would happen if you added gravity to the picture. He imagined elevators in free fall and beams of light bending near massive objects. These ideas would lead him to general relativity, a theory that explains how mass and energy warp the very fabric of space-time. But that, too, started with a thought experiment. For Einstein, imagining himself riding alongside a beam of light was more than a passing daydream. It was the key to unlocking how the universe really works. It meant letting go of the things that seemed certain and trusting the logic of the equations, no matter how strange the results appeared. When you think about it now, it's remarkable that so much of modern physics came from a young man, alone with his imagination, picturing himself gliding through space next to something that never stands still. It reminds us that curiosity is sometimes all it takes to shift the way we see reality, and that even the speed of light, something so constant and unwavering, can open the door to a universe where time and space themselves are relative. So the next time you find yourself staring out a train window or watching headlights sweep by in the dark, you might remember Einstein and his imagined light beams. You might picture yourself floating beside one, moving impossibly fast, yet always the same distance away. And in that drifting thought, you might feel, just for a moment, how wonderfully elastic time and space can be, and how a simple question can bend the world into a softer, stranger shape. Imagine standing on a quiet road at night, far from city lights, where the stars spill across the sky like grains of salt on black velvet. Now, picture a car driving toward you with its headlights on. If you stand still, you see those beams of light rushing straight toward you. If you start walking toward the car, you'd expect the light to hit you a little sooner because you're moving into its path. That's how our everyday experience works. Speeds add up or cancel out depending on how you're moving. But light doesn't behave like cars, balls, or sound waves in air. In the late 19th century, scientists were starting to learn that something was unusual about light. No matter how fast you move toward or away from a light source, its speed remains the same. This wasn't what anyone expected, because the world around us is built on the idea that motion stacks up in simple ways. If you run at 5 miles per hour toward a ball rolling at 5 miles per hour, your speed relative to the ball is 10 miles per hour. That's intuitive. But with light, this neat arithmetic falls apart. To grasp why this happens, it helps to know how we first learned to measure the speed of light. One early method came from observing Jupiter's moons. In the 1670s, the Danish astronomer Ole Romer noticed that when Earth was moving away from Jupiter, eclipses of its moon Io appeared to happen later than expected. When Earth moved closer, the eclipses seemed to occur sooner. Romer correctly reasoned that light has a finite speed, and the extra time was due to the extra distance light had to travel. This was the first evidence that light didn't move instantaneously. Later, more precise experiments measured light's speed directly in the lab. Scientists like Fizeau and Foucault used rotating mirrors to measure how long light took to travel back and forth over a known distance. The value they found, about 299,792 kilometers per second, or roughly 186,000 miles per second, became one of the most famous constants in physics. But the question remained, is that speed truly constant under all conditions? To many physicists in the 1800s, it seemed unlikely. They assumed that light, being a wave, must travel through something. Just as sound travels through air and water waves travel across the sea, light surely must need a medium. They named this invisible, all-pervasive substance the luminiferous ether. The idea was that the ether filled every part of space, even the vacuum. It would be a kind of invisible ocean in which light waves rippled outward. If that were true, then the speed of light should vary depending on your motion through the ether, like how wind affects the speed of a plane. To test this, Albert Michelson and Edward Morley set up one of the most famous experiments in science. In 1887, they used a clever device called an interferometer to compare the speed of light moving in different directions relative to Earth's supposed motion through the ether. They expected to see tiny shifts in the interference pattern as the Earth's movement changed the light's speed. But the result was shocking. They found no difference at all. Light traveled at the same speed in every direction, no matter how the device was turned. This null result puzzled scientists for years. Some tried to save the ether theory by suggesting that objects moving through the ether somehow dragged it along with them. Others proposed that objects physically shrank along the direction of motion to hide the difference, a desperate patch on an idea that no longer fit the evidence. Meanwhile, Einstein approached the problem from a different angle. He accepted the constancy of light speed as a fact, one proven by experiment, and asked what it meant for our understanding of the universe. He realized that to keep light speed constant for all observers, you'd have to let go of the idea that time and space were rigid and absolute. This was the radical leap that gave birth to special relativity. To see how strange this is, imagine you're on a spaceship moving at half the speed of light toward a distant star. You switch on a flashlight, shining its beam forward. Common sense suggests that the light should move away from you at half the speed of light, because you're already moving so quickly. But that's not what happens. The beam still moves away from you at full light speed. An observer back on Earth also sees that beam moving at light speed. No matter how fast you travel, no matter how you approach or run away from it, light keeps its speed. The universe bends its rules for everything else, but not for this. This strange behavior is deeply connected to how light works. Light is an electromagnetic wave, a disturbance in electric and magnetic fields that propagates through empty space. James Clerk Maxwell, the physicist who wrote down the equations describing electricity and magnetism, showed that these fields generate waves that always move at a speed determined by the properties of the vacuum. There's no material to slow them down or speed them up. The vacuum itself, empty as it seems, has a built-in resistance and permittivity that set this speed. So light doesn't need a carrier. It is self-sustaining. The wave keeps going because the changing electric field creates a changing magnetic field, and that changing magnetic field regenerates the electric field. An endless handoff that carries energy forward at a fixed speed. There's nothing to push or pull on, so there's no way for your own motion to affect the wave's speed. In everyday life, this constancy doesn't show up because we move so slowly compared to light. Even a supersonic jet is crawling at a fraction of light's speed. But when you start dealing with objects that move near light speed, like electrons in particle accelerators or cosmic rays from deep space, you see the effects immediately. Physicists can't ignore it because their experiments depend on it. Even your GPS navigation depends on it. The satellites that talk to your phone have to adjust for the fact that light's speed stays constant, while their high orbital speeds affect how time flows. Without these corrections, your maps would be wildly inaccurate. One way to picture how this works is to think about how the universe adjusts the numbers. If light's speed must always be the same, then distances and time intervals must stretch or shrink to keep the balance. So when you move quickly, time slows down and lengths contract along your direction of motion. This is not just a mathematical trick. It has been measured again and again. Atomic clocks flown on airplanes run slightly slower than those on the ground. Muons, tiny particles created by cosmic rays hitting Earth's atmosphere, live longer than they should because they're moving so fast that time slows for them. This is why the speed of light is often called the ultimate speed limit. As you push an object closer and closer to light speed, you have to pour in more and more energy to keep accelerating it. But no matter how much energy you add, you can never push it past that limit. The closer you get, the more time slows down for the object, and the more its length shrinks along the direction of travel. But the light itself always pulls away from you at the same speed. It's important to remember that this speed limit doesn't mean you can't move quickly. Rockets, particles, and energy beams all approach light speed in special conditions. But light, massless, self-propagating, always stays out ahead. It defines the cosmic speed limit because going faster would require infinite energy and produce contradictions in the fabric of space-time. One of the best ways to see the constancy of light's speed in action is to look at particle accelerators. In facilities like CERN's Large Hadron Collider, protons are pushed to speeds within a hair's breadth of light speed. The engineers know that they'll never reach light speed exactly, no matter how much energy they use. Instead, the protons gain more and more energy. Their mass effectively increases due to relativistic effects, but the speed approaches light speed asymptotically. It's an experimental demonstration of how nature enforces this rule without fail. This universal speed limit shapes not just how we measure motion, but how we think about cause and effect. If information could travel faster than light, it would be possible to send signals backward in time. This would break causality, the idea that a cause always comes before its effect. So the constancy of light's speed helps maintain the logical flow of events that we rely on to make sense of the universe. The next time you look at the stars, remember that the light you see has been moving at exactly the same speed since it left its source, crossing billions of miles and years of empty space without slowing down or speeding up. The light from our sun takes about 8 minutes to reach Earth, no matter how fast our planet is moving in its orbit. This constancy makes light a perfect cosmic messenger, carrying information across time and space in a way that nothing else can match. It's astonishing how much of modern technology and scientific understanding hinges on this simple but counterintuitive truth. Communications, astronomy, GPS, and high-energy physics all work because we know that light keeps its speed, unchanging, no matter what. And behind that truth lies Einstein's remarkable insight. If light refuses to adjust its speed for us, then we must adjust our understanding of space and time instead. This constant speed is not just a fact about light. It's a window into the deep structure of the universe. It reminds us that our everyday intuitions about how things move and add up are only part of the story. The universe is more precise and more surprising than our common sense suggests, and sometimes the hardest thing to grasp is not what changes, but what stays exactly the same, no matter how you chase it. Imagine you are sitting on a smooth, fast-moving train. You look out the window, and the world slides by like a painted blur. Inside the train car, though, you might set a cup of tea on the table and watch the steam drift lazily upward. If you close your eyes, you could almost believe you are sitting still, because the train moves at a steady speed along perfectly straight tracks. Nothing inside the train gives you any hint that you are moving at all. This simple observation captures the essence of an idea that lies at the heart of both classical physics and relativity: the inertial frame of reference. An inertial frame of reference is, at its core, a place where the laws of physics take their simplest form. It's a point of view where an object that feels no outside forces will continue moving at a constant speed in a straight line, or simply stay still if it was already at rest. Galileo was among the first to put this into words. Long before Einstein, Galileo imagined a ship moving smoothly across calm water. He explained that if the ship glides at a constant speed, then below deck you would have no way to tell whether you are moving or standing still. Fish swimming in a bowl, drops falling from the mast, butterflies fluttering through the cabin. All these small movements would unfold exactly the same whether the ship is docked or sailing steadily. This idea grew into one of the cornerstones of classical mechanics, the principle of relativity. For centuries, physicists recognized that motion is relative. There is no single, absolute state of rest. Instead, you must always specify motion relative to something else. A train might be moving at 60 miles per hour relative to the ground, but relative to the passengers inside, the seats and tables do not move at all. This simple notion makes it possible for us to define a frame of reference. It is like a coordinate system attached to an observer, and every measurement of motion, speed, or direction depends on the observer's chosen frame. For everyday experiences, we tend to treat Earth's surface as our default frame of reference. We say a car is moving at 50 miles per hour because we measure its speed relative to the ground. But even Earth is not truly at rest. It rotates on its axis, orbits the sun, and the solar system itself drifts through the galaxy. Yet for practical purposes, these motions are so steady and smooth that we rarely feel them. That is what makes Earth's surface an approximately inertial frame for most ordinary problems. An inertial frame has no net acceleration. That is, it doesn't speed up, slow down, or turn. If you stand in a car that accelerates forward, you feel pushed back against your seat. You know instantly that the car is not an inertial frame because your body experiences a force even though nothing visible is pushing you backward. What you feel is your body resisting the change in motion. By contrast, when the car glides at constant speed on a straight highway, you feel no such force. You could toss a ball straight up, and it would come back down into your hand just as it would if you were standing still on the side of the road. In that moment, the car acts as an inertial frame. The power of inertial frames lies in their simplicity. In an inertial frame, Newton's first law, the law of inertia, holds true without any modifications. An object in motion stays in motion unless acted upon by a net external force. This is what makes the math of physics work so well in these frames. Once you step outside them, things become more complicated. Non-inertial frames, such as a spinning merry-go-round or an accelerating car, create what we call fictitious forces or inertial forces. For example, on a merry-go-round, you feel yourself pulled outward, a sensation we call the centrifugal force. But there is no physical object pulling you. It's an effect of your frame of reference accelerating and turning. To deal with these complications, physicists introduce corrective terms in their equations when working in non-inertial frames. But in inertial frames, you don't need these extra forces. The simplicity is why physicists love inertial frames. They allow us to describe motion in its purest form. This notion plays an especially important role when we think about how light and motion interact. Before Einstein, the idea of inertial frames was already well established in classical mechanics. Newton's laws described how forces caused acceleration and how inertia kept objects moving. But the discovery that the speed of light stays constant for all observers, regardless of their motion, forced a radical rethinking of these frames. Imagine you're back on that train. If you shine a flashlight toward the front of the train, you might expect the beam's speed to be your speed plus the speed of light. But that's not what experiments show. The beam moves away from you at the speed of light, not faster, not slower, even though the train is moving. An observer standing on the ground outside the train also measures that same light beam traveling at the speed of light. Both observers, in their own inertial frames, get the same answer, even though they are moving relative to each other. This strange fact tells us that the idea of an inertial frame must be extended beyond just trains, cars, and ships. It must also include the behavior of light and time itself. In special relativity, all inertial frames are equally valid for the laws of physics, and the speed of light remains constant within all of them. To make this possible, distances and times must adjust to keep the speed of light the same for every observer. This is why observers moving at different speeds can disagree about the length of an object or the duration of an event, yet still agree on the outcome of physical laws. Einstein's insight was that you don't need to imagine some absolute, preferred frame of reference. There is no cosmic rest stop where the universe sits perfectly still. Instead, any observer moving at constant speed along a straight line, in other words, any inertial observer, has the right to consider themselves at rest. The laws of physics must look the same to them as they do to any other inertial observer. This is what makes the speed of light so special. It binds all these frames together in a consistent way. Think of satellites orbiting Earth. They are moving thousands of miles per hour relative to the surface, but they're in free fall around the planet, following a curved path due to gravity. Locally, an astronaut floating inside the satellite feels weightless, as if they are in an inertial frame. But because the orbit curves, the satellite's path is not truly inertial in the strictest sense. It's only approximately inertial for short periods or small regions. In fact, Einstein's general theory of relativity extends the idea of inertial frames even further by describing how gravity can bend the paths of these frames, warping space-time itself. The beauty of inertial frames is that they let us test our understanding of nature's laws. Whenever an experiment disagrees with the prediction, we look first to see if we chose the right frame. In particle physics, accelerators create nearly perfect inertial frames to smash particles together at high speeds. In astronomy, we often treat the solar system's center of mass as an approximate inertial frame to calculate the motion of planets. Even when we observe galaxies billions of light years away, We use the idea of a large-scale cosmic frame where the universe looks roughly the same in all directions to make sense of its expansion. In daily life, these ideas may feel abstract, yet they shape our world in subtle ways. When engineers launch a satellite, they must calculate how it will behave in its nearly inertial orbit. When pilots fly long distances, they adjust for Earth's curvature and rotation, small but measurable effects that come from the planet not being a perfect inertial frame. Even your sense of balance depends on your inner ear detecting accelerations, your body's way of noticing when you've left an inertial state. Perhaps one of the most profound lessons of inertial frames is how they reveal the relativity of motion. There is no single, universal vantage point from which to say absolutely who is moving and who is still. Instead, all motion is relative to something else. This means that rest is just another kind of motion, one that happens to match the frame you've chosen. A passenger on the train sipping tea feels still, but to an observer on the platform, that same passenger speeds by at 60 miles per hour. Both views are valid within their own frames. This simple truth can be surprisingly comforting. It reminds us that the universe does not play favorites. Whether you're standing on a platform, gliding on a train, or drifting through deep space, you can claim that your frame is at rest, and the laws of physics will agree with you. In this way, the concept of inertial frames anchors our understanding of motion, light, and time, giving us a solid foundation, even as the world we measure turns out to be far more flexible than we ever imagined. Imagine two friends standing on a train platform on a clear morning. One is staying behind. The other is about to board a special train that can reach speeds close to the speed of light. They've planned this journey as an experiment, a way to see with their own eyes what happens when time itself bends to the strange rules of the universe. The traveler climbs aboard, finds a seat by the window, and waves as the train begins to move. The platform drifts out of view, the scenery blurs, and soon the train is speeding so fast that ordinary rules no longer feel reliable. In our everyday experience, time feels steady and universal. We glance at a clock and assume everyone else's clock is ticking the same way. A second for you is a second for me. But when you look closely at how nature behaves at high speeds, that certainty begins to dissolve. Time dilation is the name physicists give to this surprising truth. The faster you move, the slower time passes for you compared to someone who stays still. This idea doesn't just come from equations. It has been tested and confirmed in experiments countless times. To understand where this comes from, picture a thought experiment that Einstein often used to explain how time behaves when you're moving close to light speed. Imagine you're sitting on that speeding train with a special kind of clock, a light clock. This clock works by bouncing a pulse of light up and down between two mirrors, perfectly aligned above and below each other. Each bounce counts as one tick of the clock. To you, sitting next to it, the pulse seems to travel straight up and straight down, ticking steadily. But to your friend standing still on the platform, the situation looks different. From the platform, the train, and therefore the clock, is moving forward at an incredible speed. So, the light pulse isn't just going up and down, it's tracing a diagonal path, like a zigzag, because the light still travels at the same constant speed for both of you. The longer diagonal path means that, from the platform observer's perspective, the pulse takes more time to complete each bounce. The moving clock ticks more slowly than the stationary one. This is time dilation in its simplest form. To the observer on the platform, your moving clock appears to run slow. This isn't an illusion or a trick of perspective. It's built into the way the universe maintains the constant speed of light for everyone. To preserve that cosmic speed limit, space and time must flex and adjust. If distances and times didn't shift, the speed of light would appear to change depending on who was measuring it, something experiments show never happens. Real-world tests of time dilation go far beyond thought experiments. One famous example involves particles called muons. Muons are created when cosmic rays hit Earth's atmosphere, producing showers of particles that travel toward the ground at speeds close to light speed. In the lab, physicists know that a muon's lifetime, how long it exists before decaying into other particles, is very short, around 2.2 microseconds. If you calculate how far they should travel before decaying, you'd expect most muons to vanish high in the atmosphere. But when scientists measure them on mountaintops and at sea level, they find far more muons surviving the trip than they should. The reason? From Earth's perspective, time for the fast-moving muons slows down, allowing them to live longer and reach the surface. Another experiment involves atomic clocks, the most precise timekeepers we have. In the 1970s, physicists put highly accurate atomic clocks on commercial jet planes and flew them around the world, comparing them with identical clocks left on the ground. When the clocks were reunited, the flying ones showed slightly less time had passed than the ones that stayed put. This tiny difference matched exactly what Einstein's theory predicts. The faster you go, the more your time stretches out, ticking just a little bit slower. It's easy to think these effects only matter when you're moving near light speed, but they're essential even for technologies we use every day. The GPS satellites that help your phone find your location orbit Earth at thousands of miles per hour. Their high speeds mean their onboard clocks experience time differently than clocks on the ground. Engineers must correct for this relativistic time dilation. Otherwise, your location could be off by miles. Tiny as the effect is, it matters because the system's accuracy depends on synchronized time signals. To see why motion slows time down, it helps to revisit the math behind the light clock. The diagonal path the light takes in the eyes of an outside observer forms the hypotenuse of a right triangle, with one side representing the distance the train moves and the other the vertical distance of the light pulse. The speed of light stays constant, so the increased path length means the time between ticks must increase. The relationship can be written using the Pythagorean theorem, leading to a factor known as gamma in special relativity. This factor depends on your speed relative to the speed of light. As you move faster, gamma grows, stretching time more dramatically. At everyday speeds, the difference is so small it's impossible to notice. But as you approach light speed, the stretching becomes enormous. This effect isn't just a curiosity. It has practical consequences for our understanding of what now means. If two people are moving relative to each other at high speed, they can disagree not just about how long an event lasts, but about the order in which events occur. One might see two events as simultaneous, while the other sees them happening one after another. This flexibility is a fundamental aspect of relativity and shows how deeply motion and time are connected. Some people wonder if this means you could travel to the future. In a sense, yes. High-speed travel is a form of time travel forward. If you could board a spaceship that flies close to light speed, you'd experience only a few years on the journey, while many more years might pass for people on Earth. When you return, you would find that the world has aged far more than you have. This is the essence of the so-called twin paradox, where one twin stays home and the other goes on a high-speed journey, only to come back younger than their sibling. The paradox is resolved when you recognize that the traveling twin switches frames of reference by turning around, breaking the symmetry of their motion. In everyday life, our speeds are so small compared to light speed that we never notice these effects. But the universe is vast, and cosmic events routinely push matter close to light speed. Particle accelerators on Earth recreate these conditions, sending protons or electrons spinning in massive rings at nearly the speed of light. In those labs, engineers and physicists must account for time dilation because it directly affects how long unstable particles last and what reactions they can observe. One fascinating implication of time dilation is that, in the view of a photon, a particle of light, no time passes at all between its emission and its arrival. Of course, a photon doesn't experience time the way we do, but according to the equations, from the photon's perspective, its journey is instantaneous, regardless of how many light years it travels. It's a reminder that at the speed of light, our familiar ideas about time break down completely. These insights reshape how we think about aging, motion, and the limits of human experience. They show that time is not a rigid backdrop against which the universe plays out, but something woven into the fabric of motion and space. When you move, you carry your own time with you, and it stretches or shrinks depending on your speed. Time dilation also hints at the unity of space and time into a single framework, space-time. Instead of thinking of them as separate, we now see them as coordinates on a four-dimensional map, connected by the speed of light. This idea, radical when it first appeared, has become a foundation for physics, used every day in calculations, engineering, and navigation. For people living their daily routines, these effects feel invisible. You could run as fast as you like and never feel your clock drift. But at the edge of what we can build, the fastest jets, the most powerful colliders, the satellites orbiting Earth, time dilation shows up in precise, measurable ways. And when we look into space, we see its consequences writ large, in particles from distant galaxies and the ticking of cosmic clocks that hint at the universe's grand scale. So next time you see a train rolling by, remember that to an observer moving quickly enough, its passengers would seem to age just a little bit slower. Time dilation is more than a strange equation in a textbook. It's a reminder that the universe keeps its secrets hidden until you move fast enough to notice them. And in that simple stretch of time, we find proof that reality is more flexible, more subtle, and more astonishing than everyday life suggests. Imagine two identical twins standing side by side on a quiet airfield at dawn. The early light casts long shadows behind them as they hug each other goodbye. One of them is about to climb aboard a spaceship capable of speeds that approach the speed of light, while the other will remain here on Earth, going about daily life. They agree to reunite when the traveler returns. The moment feels ordinary enough, a farewell between siblings. But what lies ahead is one of the strangest consequences of special relativity, a situation where time itself will treat each twin differently. This thought experiment is known as the twin paradox, and it has fascinated physicists and students alike for decades. At its heart is a simple idea. If you take a clock and move it at high speed, it ticks more slowly than a clock at rest. Since the human body can be thought of as an extremely complicated clock, moving quickly affects biological aging too. The paradox is not a contradiction in the math, but rather a puzzle for our intuition. How can two people who start out exactly the same experience different amounts of time just because one went on a high-speed journey? To see how this works, think of time dilation, the fact that moving clocks run slow. If the traveling twin boards the ship and accelerates to a speed close to that of light, they will be moving fast enough for time dilation to become significant. Let's say the traveling twin goes to a star that's many light years away, then turns around and comes back. For the person on Earth, the trip might take decades. But for the twin on the ship, the onboard clock ticks so slowly that only a few years pass. When the ship lands back at the airfield, the twin who stayed on Earth has aged decades, while the traveling twin has aged much less. It sounds strange because motion is relative. Shouldn't each twin see the other as moving? Here's where the word paradox comes in. If both motion and time dilation are relative, then you might expect that each twin sees the other as aging more slowly. But both can't be younger than the other when they reunite. The resolution lies in the fact that the situation isn't symmetrical. The traveling twin must accelerate to leave Earth, turn around at the destination, and decelerate to return. These changes of direction break the symmetry. The twin who stays on Earth remains in the same inertial frame the entire time, while the traveler does not. To make this clearer, it helps to follow each step of the journey. Suppose the star the traveler is visiting is 10 light years away, as measured from Earth. If the spaceship can travel at 99.5% the speed of light, the trip to the star takes about 10 years in Earth's frame, so the round trip is about 20 years for the stay-at-home twin. But for the twin on the ship, time passes more slowly because of the high speed. Using the time dilation formula, the traveling twin might only experience about 2 years to reach the star and 2 years to come back, a total of about 4 years. When the ship lands, the Earth-bound twin will be 20 years older, while the traveler has only aged by 4. This prediction isn't just an idea from a blackboard. It matches what we observe in real high-speed experiments, though we obviously can't send people close to light speed yet. But we do it with particles all the time. Muons created by cosmic rays hitting Earth's atmosphere, for example, travel so quickly that their internal clocks slow down, allowing them to reach the ground instead of decaying mid-air. In particle accelerators, unstable particles live longer when moving near light speed than they do at rest. The effect is real, measurable, and exactly what special relativity predicts. One might wonder, what happens during the turnaround? This is where the explanation becomes clearer. While moving at constant speed, each twin could argue the other is moving, and thus time should run slower for the other. But the moment the traveling twin turns around to head back, they switch inertial frames. Acceleration, the force that changes their direction, breaks the symmetry. The twin on Earth never changes frames. They remain in the same reference frame the whole time. This is why the traveler ends up younger. It's important to note that the actual acceleration phase, while essential for understanding the paradox, doesn't cause the age difference on its own. It's the overall difference in the paths each twin takes through space-time that matters. In physics, this is known as a proper time calculation. You add up the time experienced along each twin's path. The one who stayed home took the longer path through time. The traveler, by moving at near light speed, took a shortcut through space-time, experiencing less time than their sibling. Some students try to imagine the twins meeting halfway, but the result is always the same. The twin who undergoes acceleration and changes direction experiences less elapsed time overall. You can think of the twins' paths through space-time as lines drawn on a diagram. The straighter the path, meaning constant motion without changes in velocity, the longer the proper time. Deviations, like the traveler's turnaround, result in less elapsed time for the traveler. This paradox highlights an important lesson. Special relativity does not deny the idea of cause and effect or consistency. Instead, it shows that time and distance are not fixed and absolute. They depend on your motion. If you move quickly relative to someone else, your time literally stretches differently than theirs. You carry your clock with you, so to speak, and it keeps its own rhythm tied to your speed and path through the universe. There have even been tests on a small scale with atomic clocks flown on jets or placed on satellites. The Haffel-Keating experiment in the 1970s took atomic clocks on airplanes circling the Earth eastward and westward. When compared with clocks left behind at the U.S. Naval Observatory, the flown clocks showed time shifts that matched special relativity's predictions. The planes were not moving anywhere near light speed, so the effect was tiny, but modern atomic clocks are so precise that they can measure these differences down to billionths of a second. Another interesting aspect is that general relativity must also be considered in real-world versions of the paradox. Gravity affects time, too. Clocks in stronger gravitational fields tick more slowly than clocks farther away from massive bodies. For GPS satellites orbiting Earth, both special and general relativity must be factored in to keep navigation accurate. If engineers ignored these relativistic effects, GPS systems would drift off course by miles each day. The twin paradox, though a simple thought experiment, also opens up questions about interstellar travel. If humans ever develop ships that can cruise near light speed, travelers could, in principle, go on journeys that for them last only a few years, while centuries pass on Earth. Science fiction often explores this idea. While it doesn't allow for backward time travel, because you can't exceed light speed, it does mean that someone could jump into Earth's distant future by traveling fast enough. The real limitations are practical. Reaching significant fractions of light speed requires enormous energy. The faster you go, the more energy you need. As your speed gets closer to light speed, the energy required approaches infinity. This makes relativistic travel a technological dream for now, though one that pushes engineers and physicists to imagine what future propulsion systems might achieve. The paradox also teaches us that time is not an absolute river flowing identically for everyone. It's a dimension woven into the fabric of the universe, deeply connected to space itself. This connection, space-time, reshapes our understanding of motion, aging, and simultaneity. Events that seem to happen at the same time for one observer might not appear simultaneous to another moving observer. And biological processes like aging follow the same rules. Your heartbeat, your cells dividing, they all slow down relative to someone moving slower than you if you are moving quickly enough. So, when the spaceship touches down again on that quiet airfield, the twin who stayed behind will greet a sibling who has barely aged. It is not magic. It is not a trick of perception. It is the way the universe ensures that the speed of light remains constant for everyone, even if that means bending time itself to make it so. The twin paradox doesn't just reveal the oddities of near-light speed travel. It shows how the ideas of motion, time, and space are linked in a way that defies our everyday instincts. It reminds us that when we move, we don't just carry our bodies through space, we carry our personal timeline too. The faster we move, the more that timeline stretches and warps, and when we come back home, the clocks may no longer agree. In the end, the paradox is only paradoxical because our common sense was built for speeds much slower than light. As soon as we open our minds to the fact that the universe does not have an absolute clock ticking the same for everyone, the mystery dissolves into something even more fascinating. A world where time is flexible, motion shapes reality, and a simple journey can turn identical twins into living proof that time is not what we once thought it was. If you've ever climbed a mountain or flown in a plane, you might have noticed how your perspective on the world changes with altitude. But there's something far more subtle happening every time you change how close you are to Earth's mass. Your experience of time itself shifts ever so slightly. This effect, called gravitational time dilation, is one of the most surprising predictions of Einstein's general theory of relativity. It shows that time doesn't tick at a constant universal rate everywhere. Instead, gravity bends it, stretching and compressing it depending on where you stand in a gravitational field. To see how this works, start by picturing two identical clocks. One sits at sea level on a calm beach, close to Earth's center of mass. The other is carried up a tall mountain, many thousands of feet above sea level. To anyone watching, both clocks tick side by side. They'd appear to run at exactly the same pace. But when you compare them carefully, you find that the clock on the mountain ticks ever so slightly faster than the one at sea level. The difference is tiny, far too small to notice without precise instruments, yet it's real and measurable. The reason is that the clock on the mountain feels a weaker gravitational pull than the clock closer to the center of Earth's mass. In a weaker gravitational field, time runs faster. This idea was first hinted at through theoretical calculations in the early 20th century. Before Einstein, Newton's law of gravity explained how objects pull on each other, but it treated space and time as fixed and separate. In Newton's view, gravity was an invisible force acting at a distance, pulling planets in their orbits and apples to the ground. But Einstein's general relativity replaced this with a deeper picture. Massive objects like Earth bend the fabric of space and time around them. A planet or a star creates a dent in the cosmic fabric, and anything with mass follows the curves of that dent. Gravity, in this view, isn't just a force. It's the shape of space-time itself. If you imagine this fabric analogy, you can picture a heavy bowling ball placed on a rubber sheet, causing it to sag. Smaller balls or marbles placed nearby roll toward the heavy ball, following the curve in the sheet. Now, Add time to the picture. Not only does mass bend space, it also bends time. The closer you are to a massive object, the more space-time curves, and the more time slows down relative to regions where the pull of gravity is weaker. One of the first real-world tests of gravitational time dilation was carried out using atomic clocks. In the 1970s, physicists placed an atomic clock at the base of a water tower and another at the top, about 22 meters higher. They found that the clock at the top ticked slightly faster than the one below, in precise agreement with Einstein's equations. Later, much more accurate tests used towers, aircraft, and even satellites to confirm the effect. The results showed that time genuinely runs differently depending on your position in a gravitational field. It's not only experiments on Earth that demonstrate this. The effect becomes dramatic near incredibly dense objects like neutron stars or black holes. Near the surface of a neutron star, gravity is so intense that time slows significantly compared to Earth. The deeper you go into a massive gravitational well, the slower time passes relative to an observer farther away. This means that if you could hover safely near the event horizon of a black hole, the point of no return, and then return to Earth, you would find that much more time had passed for people far from the black hole than for you. This is no science fiction twist. It's a direct result of how gravity warps the flow of time. The idea can feel almost impossible to grasp because in our daily lives, gravity feels so ordinary. We're used to thinking of it as the reason things fall to the ground, the force that keeps our feet planted, or what makes balls arc through the air. But the same force shaping the motion of falling objects also shapes the rhythm of seconds and minutes. Each moment you spend closer to a massive object, your heartbeat, thoughts, and aging proceed just a touch slower relative to someone farther away. This effect is more than a theoretical curiosity. It plays a crucial role in technologies we depend on every day. The Global Positioning System, or GPS, relies on a network of satellites orbiting Earth at altitudes of around 20,000 kilometers. The satellites carry extremely precise atomic clocks to time their signals, which your phone or GPS receiver uses to calculate your position. Those clocks are farther from Earth's mass than you are on the surface. That means they experience weaker gravity, so their onboard clocks run slightly faster than clocks on the ground. If engineers ignored this difference, GPS readings would drift by about 10 kilometers each day, making the system useless for navigation. To fix this, the satellite's systems adjust their time signals to account for gravitational time dilation. They also correct for the time dilation caused by the satellite's high speeds, which slow their clocks down. A special relativity effect that works in the opposite direction to the gravitational effect. These corrections are so precise that they demonstrate how deeply intertwined gravity and time have become in our understanding of the universe. What used to be an abstract concept, the flow of time being bent by mass, is now built into the electronics that help you find your way to a new restaurant or track a package arriving at your door. In everyday settings, the differences are so slight that we never notice them. A person living in a valley ages just a tiny bit more slowly than someone who spends their whole life on a mountaintop, but the difference over a lifetime would be measured in nanoseconds, fractions of a second. It's only when you begin to look at extreme gravitational environments that the effect becomes dramatically clear. Perhaps the most striking example comes from black holes, where gravity is so strong that space-time curves inward completely. Near the event horizon of a black hole, time dilation becomes immense. From the viewpoint of a distant observer, a clock falling toward the event horizon appears to tick slower and slower, almost freezing as it approaches the boundary. To the falling object, time feels normal. Seconds pass in a steady rhythm. But an outside observer would see those seconds stretch toward infinity. Light escaping from close to the event horizon is also stretched, shifting to longer wavelengths in a process known as gravitational redshift. These predictions have been confirmed by observing how light behaves near massive stars and compact objects. Astronomers can even see gravitational time dilation when they study light from white dwarfs and neutron stars. In 1959, physicists Robert Pound and Glenn Rebka carried out a landmark experiment at Harvard University to test this effect on Earth using gamma rays. They sent gamma-ray photons up and down a tower and measured how the frequency of the light changed due to Earth's gravitational field. The tiny redshift they observed matched general relativity's predictions exactly. Gravitational time dilation also plays a role in the lives of satellites, astronauts, and future space missions. The International Space Station orbits about 400 kilometers above Earth's surface, where the gravitational pull is slightly weaker than on the ground. This means that, due to gravity alone, astronauts' clocks tick faster than ours. However, because they're also moving at high speed, special relativity kicks in too, and the high orbital speed slows their clocks down. In the case of the ISS, the speed effect is larger than the gravity effect, so the astronauts actually age slightly less than people on Earth. This delicate balance between special and general relativistic effects is an everyday reality for people designing satellite systems. Even tiny errors matter. The fact that we can measure and correct for these differences so precisely is a testament to how robust our understanding of relativity has become. When we think of the universe as a whole, gravitational time dilation shapes our view of distant objects and events. For example, some massive black holes at the centers of galaxies bend time so dramatically that light from material falling into them appears to slow down as it gets closer to the event horizon. This gives astronomers a window into extreme physics, allowing them to test theories of gravity in some of the most hostile environments imaginable. One way to think about gravitational time dilation is to imagine the fabric of space-time as a landscape, where there's a lot of mass, like a planet, star, or black hole. The landscape dips down, forming a valley. The deeper you go into that valley, the slower your clock runs relative to someone on a higher ridge. This means that gravity doesn't just pull you downward, it also pulls on time, stretching it out the closer you get to the source of mass. This stretching of time affects everything that relies on precise timing, from the decay of particles to the evolution of stars. It even shapes our understanding of the age of the universe. When scientists measure the light from distant galaxies, they must account for how gravity and the expansion of the universe stretch the signals that reach us, shifting not just wavelengths, but our perception of time scales too. So, whether you're standing at sea level, flying on a jet, or imagining hovering near a black hole, gravity's influence on time is always there, gently shaping the passage of seconds in ways that are invisible but deeply real. It reminds us that time is not an unchanging backdrop, but a dynamic part of the universe, woven together with space and mass. The next time you stand on a hill and look down at the world below, you might remember that, in a way, your heartbeat ticks just a tiny bit faster than it would in the valley, a subtle testament to the way gravity and time are forever linked. Picture the darkest place you could ever imagine, a region of space so extreme that nothing, not even light, can escape its grasp once it crosses an invisible threshold. This is a black hole, a place where the warping of space-time becomes so severe that the normal rules we rely on in daily life fall apart. The most fascinating aspect of a black hole isn't just that it pulls things inward with tremendous force. It's how it distorts time itself for anyone nearby. Understanding how time behaves near a black hole's edge offers one of the clearest windows into the strange predictions of general relativity. To see why this happens, it helps to begin with how a black hole forms. Imagine a massive star, many times heavier than our Sun, reaching the end of its life. When it runs out of fuel, it can no longer produce the outward pressure that balances gravity's inward pull. The core collapses under its own weight, compressing matter into an incredibly dense point known as a singularity. Around this singularity lies the event horizon, the boundary that marks the point of no return. Anything that crosses this boundary, particles, light, or even information, cannot escape. From outside, the event horizon appears as a perfectly spherical surface, with no solid barrier, but crossing it seals an object's fate. Now, consider what happens to time for an observer hovering just outside that boundary. To someone far away, say, floating safely at a great distance from the black hole, a clock held by this closer observer appears to slow down drastically. This is gravitational time dilation pushed to its extreme. The closer you are to the massive center, the more space-time is curved, and the more time stretches compared to someone far from the mass. From the faraway observer's point of view, it takes an infinite amount of time for anything to reach the event horizon. They would see the falling clock ticking slower and slower, its signals stretched and shifted to longer wavelengths, until they fade into invisibility. Yet, for the person falling toward the event horizon, time feels perfectly normal. If you were that observer drifting closer, your heart would beat, your thoughts would race, and your clock would tick just as they always do. The difference is that from your point of view, the rest of the universe seems to speed up. Looking back toward the stars, you'd see the entire history of the outside world racing by faster and faster as you approached the horizon. This extreme difference shows how relative time can be under strong gravity. A classic way to picture this is to imagine an astronaut falling feet first toward a black hole. Suppose they shine a flashlight back to a spacecraft hovering safely in orbit. To the people in the ship, the flashes of light come at longer and longer intervals as the astronaut gets closer to the event horizon. The light waves stretch out, becoming redder and weaker, a phenomenon known as gravitational redshift. Eventually, the signal fades altogether. To the crew on the ship, it seems as though their colleague never actually crosses the event horizon. The astronaut appears frozen in time, hovering forever just outside. But for the astronaut, there's no barrier to feel. Once they pass the event horizon, they're committed to falling inward. their clock keeps ticking normally, and they'd reach the singularity at the center in a finite amount of their own time. The contradiction, appearing frozen to an outside observer but feeling normal motion themselves, is one of the strangest parts of black hole physics. Scientists have tested aspects of this behavior by observing light near extremely dense objects. While we can't watch someone fall into a black hole, we can measure how light behaves as it escapes powerful gravitational wells. When astronomers study stars orbiting close to a supermassive black hole at the center of our galaxy, they see light redshifting and signals lagging exactly as general relativity predicts. These observations match the idea that gravity can slow time dramatically. This time-warping effect becomes more than just a curiosity when we think about extreme environments. For example, the Event Horizon Telescope's first image of a black hole's shadow in 2019 showed how light bends around the black hole's edge, creating a ring of glowing gas swirling just outside the event horizon. The gas is heated to millions of degrees and emits radiation that must escape the intense gravitational pull. As it does, the light's frequency shifts, and the time it takes for those signals to reach Earth is altered by the curved space-time around the black hole. In more practical terms, the physics of black holes and time dilation play a role in astrophysics research. When we look at quasars, distant, extremely bright objects powered by supermassive black holes, we are witnessing light that has been warped, delayed, and stretched by the intense gravity of the black hole and its surrounding disk. The signals we detect have taken millions or billions of years to reach us, and the extreme conditions near the black hole affect how that light encodes information about the object's size, mass, and spin. Gravitational time dilation near a black hole is an extension of the same principle you'd see on Earth, just amplified to the limit. On Earth, the effect is so slight you'd never notice it in daily life, but near the event horizon, the warping becomes so intense that time essentially stands still for the infalling object, relative to distant observers. This effect isn't just theoretical. It's built into equations that match what we see when we study the behavior of stars, gas, and radiation near these cosmic giants. The mathematics behind this comes from the Schwarzschild solution, a solution to Einstein's field equations that describes the space-time geometry around a spherical, non-rotating mass like a simple black hole. The solution predicts how time behaves at different distances from the mass. As you approach the event horizon, the time dilation factor grows infinitely large, showing that from an external frame, you'd never quite see an object cross the horizon. For rotating black holes, described by the Kerr solution, the situation becomes even more complex. The rotation drags space-time around with it, a phenomenon called frame dragging, which further affects how time flows for anything caught near the rotating mass. Even beyond the event horizon, general relativity predicts that all paths lead to the singularity at the center, a place where our current understanding of physics breaks down. Time, space, energy, and matter collapse into a region of infinite density. What happens there is unknown because the laws of physics, as we know them, cannot fully describe such conditions. This is one reason why black holes remain one of the great frontiers in theoretical physics. One famous way to illustrate this bending of time is through thought experiments. Physicists like Kip Thorne have used these scenarios to help people grasp what it means to hover near an event horizon. In science fiction, you often see plots where a crew ventures near a black hole and comes back to find centuries have passed in the outside universe, while only a few years have passed for them. This is rooted in the real, measurable physics of gravitational time dilation. While traveling near a black hole's event horizon poses insurmountable challenges, the underlying concept holds true. As strange as all this sounds, there are indirect ways we observe these effects in nature. When two black holes spiral toward each other and merge, they send out ripples in space-time called gravitational waves. The detection of these waves by observatories like LIGO relies on clocks so precise that they can spot distortions in time passing by as tiny fractions of a second. These distortions match predictions of general relativity, showing that time and space are flexible and dynamic, not fixed backdrops. The study of black holes and time dilation doesn't just expand our understanding of gravity, it pushes the limits of what we know about the universe. It suggests there may be conditions where time can be stretched to extremes, or where the very nature of space-time must be reimagined through a new theory that unites general relativity with quantum mechanics. Efforts to develop a theory of quantum gravity, such as string theory or loop quantum gravity, are partly driven by the mysteries that arise when you try to understand what happens deep inside a black hole. When you look at the night sky and spot the faint glow of galaxies, remember that at the heart of many of them lie supermassive black holes, each one distorting the passage of time around it. The light we see has often traveled millions of years to reach us, carrying information that has been shaped by the extreme gravity along its path. In this way, the universe itself becomes a vast laboratory for observing how time and gravity dance together. Gravitational time dilation near a black hole is a reminder that time is not a simple, steady current flowing the same way for everyone, everywhere. It bends and stretches in response to the presence of mass and energy, following the geometry of space-time described by Einstein's equations. In the end, it teaches us that the reality we take for granted, the steady tick of the second hand, is only one version of time's rhythm, shaped by our position in the cosmos. Near the edge of a black hole, that rhythm slows until, to the rest of the universe, it almost stops, showing just how flexible and astonishing time can be. Imagine standing on a quiet train platform, looking at two clocks, one at each end of the platform. Let's say they're perfectly synchronized. If a bolt of lightning strikes both ends at the same instant, you, standing right in the center, see both flashes at the same time. It seems obvious to you that the strikes were simultaneous. The word itself means occurring at the same time. But what if someone is moving past the platform at high speed? Would they see the same thing? This simple scenario reveals a strange truth. Whether two events happen at the same time depends on how you're moving. This is called the relativity of simultaneity, and it's one of the core ideas that makes special relativity so different from the physics of everyday life. The idea that simultaneity is relative comes directly from the constancy of the speed of light. Einstein realized that for light's speed to remain the same for all observers, our understanding of time must bend. He often explained this with the thought experiment about a moving train and a lightning strike. Suppose you're riding inside the train, which is moving at a constant high speed along the tracks. At the exact moment you pass the person standing on the platform, lightning strikes both ends of the train. The person on the platform sees the flashes reach them at the same instant, so they conclude the strikes were simultaneous. But for you, sitting inside the train and moving forward, the situation looks different. Because the train is moving in the direction of one lightning strike and away from the other, the light from the strike ahead of you has less distance to cover than the light from the strike behind you. Yet the speed of light must remain constant for you too. So, to keep the rules consistent, you must conclude that the strike ahead happened before the one behind. What's simultaneous in one frame isn't simultaneous in another. This result feels counterintuitive because our brains evolved for life at human speeds, where the effects are imperceptible. If two friends clapped their hands at opposite ends of a room, you'd say they clapped at the same time. But light travels so fast compared to the distances in your room that any difference in travel time is negligible. Only when you approach speeds close to that of light, or consider vast distances, does the relativity of simultaneity show its true colors. One way physicists make sense of this is by defining events in space-time. An event is something that happens at a specific place and time, like a lightning strike or a clock ticking. You can plot events on a diagram, with one axis representing time and another representing position in space. In classical physics, all observers would agree on the order of events and which ones were simultaneous. But with special relativity, the tilt of your reference frame depends on how you're moving. This tilt shifts which events line up horizontally. In other words, which ones you judge to be happening at the same time. The consequences of this idea go deeper than a train and a lightning bolt. Imagine two astronauts floating far apart in deep space, both at rest relative to each other. They each turn on a flashlight at what they agree is the same instant. Now, suppose a spaceship flies by at high speed. The crew on the spaceship will see the astronauts turn on their flashlights at different times, because, from the ship's perspective, the flashes are not simultaneous. The disagreement doesn't mean anyone is wrong. It means simultaneity itself depends on the observer's state of motion. This is more than just a quirk of perspective. It's built into the structure of how time and space fit together. The relativity of simultaneity leads directly to time dilation and length contraction. If you change your motion, you change how slices of space-time line up in your frame. Time and space merge into a single four-dimensional fabric, space-time. One observer's now is not another's now. The notion of a single universal present that applies everywhere is no longer valid. This is part of what made special relativity so radical. These effects, though invisible in daily life, have practical consequences in modern technology and physics. Take the GPS system again. Satellites orbit Earth at high speeds and different gravitational potentials than receivers on the ground. To keep their clocks accurate, engineers have to account for both special and general relativistic effects. Part of this means understanding that the notion of synchronized time depends on your frame. The signals sent down to your phone must be adjusted for the fact that now in orbit is not quite now on Earth. Physicists also use the relativity of simultaneity when modeling particles in accelerators. Particles moving near light speed experience time and space differently than lab equipment at rest. Predicting when collisions will occur requires translating between frames, ensuring that the calculations respect the fact that simultaneity shifts when you change your speed. One famous thought experiment highlighting this principle is the ladder paradox. Imagine a long ladder moving at relativistic speed toward a barn shorter than the ladder. From the barn's frame, length contraction makes the ladder short enough to fit entirely inside for a brief moment. But from the ladder's frame, it's the barn that contracts, and the ladder should never fit inside completely. How can both be true? The resolution is that the question of whether the ladder is entirely inside depends on simultaneity. In the barn's frame, both ends of the ladder can be inside at the same time. In the ladder's frame, the back end is still sticking out when the front hits the back wall, because the same time slices differ in each frame. This shift in simultaneity also shows up when considering signals sent between moving spaceships. If two ships fly past each other at high speed and flash lights as they pass, observers on each ship will disagree on which signals line up in time. What seems like a perfect handshake from one perspective becomes staggered when viewed from another moving frame. Again, no contradiction arises. It's simply how nature preserves the constancy of light speed and the consistency of physical laws. A striking aspect of this idea is that it challenges our instinctive belief in a shared now. In Newtonian physics, time is absolute, flowing uniformly for all observers. But in special relativity, the simultaneity of distant events becomes a fuzzy concept. If you watch two stars exploding on opposite sides of the galaxy, you might say they went supernova at the same time. Yet an alien traveling between the stars at high speed could record that one exploded before the other. Both accounts are valid in their own frames. The fact that simultaneity is relative does not break causality. Cause and effect relationships remain preserved. Events that are causally connected, one causes the other, always happen in the same order for all observers, regardless of motion. This is because no information or influence can travel faster than light. So, while distant, unrelated events can shuffle around in time depending on the observer, causal links stay intact. This rule keeps physics consistent and prevents logical paradoxes like backward time travel. To see how simultaneity connects with everyday experience, think about how signals and information move. If you could instantaneously know what's happening everywhere at once, you'd violate the speed of light limit. But because all signals take time to travel, our sense of now is always local. What you see in the night sky is the past. The light from distant stars began its journey millions or billions of years ago. The universe is filled with moments happening on their own timelines, stitched together by the finite speed of light. Astronomers routinely account for this when they measure cosmic events. When telescopes detect light from a galaxy, they know they're seeing how it looked eons ago. In that time, the galaxy may have merged with others, formed new stars, or even disappeared altogether. Our view is a snapshot frozen by the speed at which information crosses the vast distances of space. In theoretical physics, the relativity of simultaneity is woven into the design of space-time diagrams, which help visualize how events are ordered for different observers. These diagrams tilt depending on the observer's speed, showing how slices of now shift with motion. For an observer at rest, lines of simultaneity are horizontal. For someone moving, the lines tilt, revealing that what's simultaneous for one may not be for another. Though the principle seems abstract, it's one of the best examples of how special relativity challenges our intuitions. It teaches us that the universe does not revolve around a single cosmic clock. Instead, each observer carries their own definition of now, shaped by their motion through space. What we take for granted as a universal moment is, in reality, a patchwork of perspectives that only match when everyone is at rest relative to each other. So next time you watch a train pull into a station, see a plane fly overhead, or imagine signals traveling through deep space, remember that every motion subtly reshapes what now means for each observer. Light's unwavering speed holds this structure together, forcing time and space to bend in ways that keep the universe consistent yet endlessly surprising. The relativity of simultaneity is a reminder that our daily sense of time's flow is just one version of a more flexible reality. It invites us to see that time and space are not rigid but adaptable, adjusting themselves to ensure the rules of nature remain the same for everyone, no matter how fast they're moving. In this simple but profound way, it shows us that the universe is stitched together by light, and that our place within its tapestry depends not only on where we are, but on how we move through it. When you look up at the night sky and see the moon hanging above the horizon, it's easy to think of it as a ball orbiting Earth because Earth's gravity is pulling on it. For centuries, that's how people explained why planets circle the sun and why the tides rise and fall. Isaac Newton's law of universal gravitation described gravity as a force acting at a distance, pulling objects together according to their masses and the square of the distance between them. It was a brilliant idea, and it worked so well that it guided everything from predicting eclipses to planning space missions for hundreds of years. But in the early 20th century, Albert Einstein saw that Newton's picture, as powerful as it was, couldn't fully explain some subtle observations about how gravity really works. So he asked a deeper question. What if gravity isn't a force at all, but instead something more like a shape? To understand what he meant, think about how objects move when nothing is pushing or pulling on them. In space, if you throw a ball, it will keep moving in a straight line forever unless something gets in its way. This idea, known as inertia, was one of Newton's key insights. Objects naturally move along straight paths unless a force changes that path. But Einstein wondered what straight means if space itself can curve. His insight was that space and time are not separate things, but are joined together into a single four-dimensional fabric called space-time. In this fabric, mass and energy can bend and stretch the geometry itself. So instead of a force reaching out across empty space, gravity is the effect of objects following the curved paths that this fabric creates around massive bodies. In this view, Earth moves around the sun not because the sun is tugging at it with an invisible string, but because the sun's mass warps the fabric of space-time, and Earth's motion naturally follows the curve of that warp. A common way to picture this idea is with the rubber sheet analogy. Imagine a large, flexible sheet stretched tight, like a trampoline. If you place a heavy bowling ball in the middle of the sheet, it will sink down, creating a dimple. Now roll a marble across the sheet near the bowling ball. The marble's path curves inward, not because the ball reaches out and pulls on it, but because the surface itself is bent. In a rough sense, this is how space-time behaves around massive objects. Planets, stars, and black holes all create dents in the fabric, and other objects follow the curves of those dents. The beauty of this idea is that it explains phenomena that Newton's theory couldn't fully account for. One famous example is Mercury's orbit around the Sun. Astronomers had long noticed that Mercury's path didn't match up perfectly with Newton's predictions. Its elliptical orbit precessed, meaning the point closest to the Sun shifted slightly over time, more than expected. Einstein's equations showed that the Sun's massive gravitational field warps space-time so strongly near Mercury that the planet's path naturally drifts in exactly the way astronomers observed. It was one of the first major successes of the general theory of relativity. But the real test came in 1919 during a total solar eclipse. Light from distant stars passes near the Sun on its way to Earth. If the Sun's mass curves space-time, then the starlight should follow that curve, appearing to bend around the Sun. During the eclipse, when the Sun's light was blocked, astronomers measured the positions of stars near the Sun's edge. They found that the stars' apparent positions shifted just as Einstein's equations predicted. This bending of light is called gravitational lensing, and it's one of the clearest pieces of evidence that mass really does shape the geometry of space-time. The idea that light itself can be bent by gravity is astonishing when you first hear it. Light always travels along the straightest possible path through space-time. But when space-time is curved, those straight paths, called geodesics, are themselves curved. So light appears to bend around massive objects, not because it's being pulled by a force, but because it's following the natural curves of a warped fabric. This bending has practical consequences in astronomy today. When scientists look at distant galaxies, they often see distorted arcs or rings of light around massive clusters of galaxies. These clusters act as gravitational lenses, bending the light of even more distant galaxies behind them. This effect lets astronomers study objects that would otherwise be invisible and measure the distribution of mass, including dark matter, which doesn't emit light but does bend space-time. The notion that space-time can bend also explains why time itself runs differently in different gravitational fields. Near a massive object, the stretching of space-time affects not only distances, but also the passage of time. A clock on Earth's surface runs a tiny bit slower than one far above Earth, because the planet's mass curves space-time around it. This is why GPS satellites must adjust their onboard clocks for both the effects of gravity and their speed through space. Even though the time differences are tiny, ignoring them would cause navigation errors to build up quickly. Thinking of gravity as geometry reshapes the way we imagine motion. A satellite orbiting Earth is not constantly being pulled inward by some invisible rope. Instead, it is in free fall, always moving along the curved space-time created by Earth's mass. The satellite wants to move in a straight line, but in curved space-time, that straight line is an orbit, a circular or elliptical path that follows the dent in the fabric. The same principle holds for the Moon orbiting Earth, Earth orbiting the Sun, and stars orbiting around the centers of galaxies. This curved fabric view also reveals what happens when massive objects collide. When two black holes spiral into each other and merge, they create ripples in space-time called gravitational waves. These waves are like the vibrations on a stretched sheet when you pluck it. In 2015, scientists at the LIGO Observatory directly detected these waves for the first time, confirming yet another of Einstein's predictions. Gravitational waves stretch and squeeze space-time as they pass, and the detectors measure these tiny changes, shifts smaller than the width of an atomic nucleus, proving that space-time is indeed flexible and dynamic. One of the most mind-bending implications of space-time curvature is the existence of black holes. When enough mass is packed into a small region, the bending becomes so extreme that it forms a region from which not even light can escape. The event horizon marks the boundary where the inward curve is so steep that all paths lead deeper in. Beyond that point, space-time curves inward completely toward the singularity, where our current theories reach their limits. Physicists believe that to fully understand what happens at the singularity, we'll need a quantum theory of gravity, a framework that combines general relativity with quantum mechanics. Beyond black holes, space-time curvature shows up on cosmic scales too. The entire universe's shape depends on its total mass and energy content. Cosmologists study whether the universe is flat, uncurved on large scales, positively curved like the surface of a sphere, or negatively curved like a saddle. Observations so far suggest that the universe is very close to flat, meaning its overall geometry is balanced. This shape affects how the universe expands, how galaxies form, and what its ultimate fate may be. The equations that describe how mass and energy bend space-time are called Einstein's field equations. They are not simple formulas, but a set of interlinked equations that relate the curvature of space-time to the energy and momentum of whatever matter or radiation is present. Solving these equations for different situations gives us predictions about black holes, expanding universes, gravitational waves, and much more. For physicists, thinking in terms of space-time geometry has become second nature. When they calculate how a spacecraft will navigate around a planet, they're really calculating how it will follow the curved geodesics of the local space-time. When they design experiments to test relativity, they look for signs that space-time bends in ways the equations predict. Yet for most of us, the idea that the universe's structure can stretch and bend remains deeply surprising. It means that space is not an empty stage where events unfold. It's an active participant, shaped by what it contains and influencing how things move. Even the passage of time is woven into this fabric, stretched or squeezed by the presence of mass and energy. The next time you watch the moon drift across the night sky or see a planet appear just before dawn, you might remember that you're watching objects tracing out paths through a curved space-time landscape, following the geometry shaped by the sun, Earth, and the cosmic neighborhood beyond. It's a quiet reminder that the world we move through every day is more flexible and interconnected than our senses can reveal. Gravity is not merely a force pulling us down to the ground. It is the shape of the very stage on which we live our lives, a stage that bends, flexes, and ripples under the weight of everything it holds. When you first hear that gravity is not really a force in the traditional sense, but instead the result of curved space-time, it can sound abstract and difficult to picture. To make this idea easier to grasp, physicists and teachers often turn to one of the most famous visual aids in science, the rubber sheet analogy. This simple image has helped countless people form a first mental model of how general relativity describes the universe, even if it doesn't capture every detail of the mathematics behind it. Imagine you stretch a large rubber sheet tight across a frame, like a trampoline or a flexible membrane. This sheet represents the fabric of space-time, the combined entity of space and time woven together into a four-dimensional whole. In this picture, the sheet by itself is flat, with no dips or curves. If you roll a small marble across the surface, it moves in a straight line at constant speed because there's nothing to change its path. This represents how, in the absence of any mass or energy, Objects in space-time move in straight lines forever. Now, suppose you place a heavy ball, like a bowling ball, in the center of the sheet. The weight of the ball sinks down into the membrane, creating a depression around it. If you now roll the marble across the sheet, its path curves inward as it passes near the bowling ball. From above, it looks like the marble is being pulled toward the heavy ball, but in reality, the marble is just following the curve of the sheet. This is the essence of general relativity. Mass bends space-time, and objects respond to that bending by following curved paths, even though locally they are moving straight ahead according to their own inertia. This analogy helps explain why Earth orbits the Sun. The Sun's immense mass creates a deep well in the fabric of space-time. Earth, moving at its orbital speed, is constantly falling inward along this curved surface, but keeps missing the Sun because its sideways motion keeps it on a looping path around the depression. In other words, Earth's orbit is simply the result of it moving along a curved geodesic, the straightest possible path in a curved space. One thing the rubber sheet analogy makes clear is that the more massive an object is, the deeper the well it creates. A planet like Jupiter makes a shallower dent than the Sun, while a black hole compresses its mass so tightly that it creates a pit so deep and steep that nothing can climb out once it crosses a certain boundary. This boundary is known as the event horizon, and it marks the point where the slope of the well becomes infinitely steep. Even light, which always moves at the same speed locally, cannot escape because all paths curve inward once inside the horizon. The rubber sheet also offers a first way to think about gravitational lensing. If you roll a marble past the heavy ball, its path bends around the dent and continues on a new trajectory. In space, when light from a distant galaxy passes near a massive cluster of galaxies or a black hole, its path bends in a similar way, creating arcs or multiple images of the same distant object. This effect lets astronomers observe objects that would otherwise be hidden or too faint to see directly. However, like any analogy, the rubber sheet has its limits. One of its biggest shortcomings is that it uses gravity, the very thing it's trying to explain, to illustrate how the sheet bends. On Earth, the bowling ball sinks into the rubber sheet because Earth's gravity pulls it downward. But in real space-time, there is no external force acting to push mass into a depression. Instead, mass and energy cause space-time to curve naturally, according to Einstein's field equations. The sinking is not a pull from another direction, but an intrinsic property of space-time itself. Another limitation is that the sheet represents only 2 dimensions of space. The real universe is 4-dimensional, with 3 spatial dimensions and 1 time dimension intertwined. The sheet can't show how time bends along with space, or how the warping of time contributes to phenomena like gravitational time dilation. For example, a clock closer to the massive object in the rubber sheet model doesn't visibly tick slower on the sheet. But in real space-time, time itself is stretched near massive objects. Still, despite these limitations, the rubber sheet remains a powerful teaching tool because it provides an intuitive visual bridge between the familiar world and the more abstract realm of curved space-time. It helps people picture why objects follow paths that look curved, even though no force acts at a distance to tug on them in the way Newton imagined. This idea of curved paths extends to everyday satellites in orbit around Earth. Think of a communications satellite circling high above. It stays in its orbit not because rocket engines constantly push it, but because it's moving along the natural curved path defined by Earth's space-time well. It's in continuous freefall, always moving sideways fast enough that it keeps missing Earth's surface. This same concept applies on larger scales. Stars orbiting within a galaxy trace out paths determined by the gravitational landscape created by all the other stars, clouds of gas, and the mysterious dark matter that surrounds them. In places where there's more mass, and thus deeper wells, stars move faster to stay in orbit, just as a marble speeds up when it rolls closer to the center of the rubber sheet's depression. When scientists study how galaxies bend light, they can even map the invisible parts of this landscape. For example, if the observed lensing effect is stronger than what visible matter can account for, that suggests there's additional mass bending space-time, mass we can't see directly. This is how gravitational lensing has become one of the best tools for studying dark matter. Beyond lensing and orbits, the rubber sheet analogy hints at another fascinating aspect of general relativity: the idea that distortions in the fabric can ripple outward. If you jiggle the heavy ball, it sends waves through the sheet. In real space-time, when massive objects accelerate, like two black holes spiraling into each other, they create ripples in space-time called gravitational waves. These waves stretch and squeeze the distances between objects as they pass by, but the effect is tiny. The detectors built to find them, like LIGO and Virgo, are so sensitive they can measure changes smaller than the width of a proton. The first direct detection of gravitational waves in 2015 confirmed that these ripples really do carry energy across the cosmos, further proving that space-time is not just a static backdrop, but an active, dynamic fabric. All this emerges from Einstein's deceptively simple insight that gravity is geometry. His field equations describe how matter and energy tell space-time how to curve, and how that curvature tells matter how to move. In the rubber sheet analogy, the curve comes from the ball, and the path of the marble comes from the shape of the sheet. In the real universe, it's the same. Planets, stars, black holes, and even light all follow the contours of this flexible, four-dimensional terrain. The everyday effects of this can be subtle, but real. For instance, engineers planning satellite launches must account for how Earth's gravitational well affects a satellite's trajectory. Clocks on the surface and in orbit tick at slightly different rates because the depth of the well changes how time flows. The satellite's speed contributes too, so both special and general relativity corrections are needed to keep systems like GPS accurate. Even the future of the universe is tied to how this fabric stretches. Cosmologists study the shape and expansion of space-time on the largest scales to understand how galaxies move apart and what might happen billions of years from now. The universe might keep expanding forever, slow to a halt, or reverse, all depending on the mass, energy, and curvature of space-time itself. When you stand on the ground and feel your weight pressing you downward, you're not experiencing an invisible pull, but rather following the curved path your body naturally takes through Earth's space-time dent. If you jump, you follow an arc that your momentum and the shape of the well define. Every motion, from a baseball thrown through the air to light from a distant star bending around a galaxy cluster, reflects the same rule. Matter and energy shape the terrain, and everything else moves according to that shape. The rubber sheet image may be a simplified glimpse into this hidden structure, but it invites us to see gravity not as a mysterious action at a distance, but as a gentle shaping of the stage on which every story in the universe unfolds. It reminds us that we live on a planet cradled within a depression in space-time, orbiting a star that curves the fabric further, all of it nested within the vast, curved web of a universe that bends and ripples under the weight of every atom and every burst of light. Though the real equations are far more complex than a stretch of elastic cloth, the core idea remains beautifully clear. The universe is flexible, shaped by what it contains. In this subtle curvature, we find the key to understanding orbits, light bending, the slowing of clocks, and the dance of galaxies. It all starts with a simple image: a sheet stretched tight, a heavy weight pressing down, and a tiny marble rolling along the path the shape creates. A small window into the deep, elegant truth that the fabric of reality is never perfectly flat, but always shaped by the things that live within it. When you hear about black holes, you might first imagine them as giant cosmic vacuums, devouring everything that drifts too close. But the most remarkable thing about a black hole isn't just how strongly it pulls. It's what happens to time itself in the space around it. General relativity shows that near a massive object, time runs more slowly than it does farther away. A black hole is simply an extreme case of this principle, taken to its furthest limit. For anyone watching from far away, time near the edge of a black hole appears to slow almost to a halt. To see how this works, it helps to start with how mass affects time in general. When Einstein introduced general relativity, he showed that massive objects like Earth or the Sun bend space-time around them. This bending affects not only the paths objects take through space, but also the rate at which time passes. The stronger the gravitational field, the deeper you are in the gravitational well. The slower your clock ticks compared to someone far away. We see this effect even on Earth. A clock at sea level ticks ever so slightly more slowly than a clock on a mountaintop, because the mountaintop clock sits higher in Earth's gravitational field and feels a weaker pull. With a black hole, the difference becomes dramatic. A black hole forms when a huge amount of mass collapses into an incredibly small region. The result is an object so dense that its gravitational pull bends space-time inward steeply. Around every black hole is an invisible boundary called the event horizon. This is the point of no return. Once anything crosses it, a particle, a spaceship, even light, it cannot escape. The curvature of space-time is so extreme that all paths forward lead inward. But to an outside observer, the truly fascinating thing is what happens just outside that edge. Imagine an astronaut falling toward a black hole while sending out regular light pulses back to their friend watching from a safe distance far away. At first, the pulses arrive steadily, one every second, let's say. But as the astronaut drifts closer to the event horizon, the pulses take longer to reach the observer. The wavelengths stretch out, becoming redder and weaker. This effect, called gravitational redshift, is a direct sign that time is slowing down near the black hole's edge. From the astronaut's perspective, their clock ticks normally. They see the pulses go out one after another, and their heart beats at its usual rhythm. But to the distant observer, each pulse arrives later than the last. In fact, As the astronaut approaches the event horizon, the intervals between pulses stretch out to infinity. From far away, it seems like the astronaut never actually crosses the event horizon. They appear frozen at the edge, fading ever more slowly from view. This freezing is not just a trick of the eye, it's a real difference in the flow of time between the two perspectives. For the falling astronaut, time feels unchanged. They pass the event horizon and continue inward in a finite span of their own time. But to the person observing from a distance, time for their friend near the horizon appears to slow to a crawl. To understand why this happens, you can think of the black hole as creating a steep gravity well in space-time. The closer you are to the center, the deeper you are in the well. To escape from deeper down, light must climb out, stretching its wavelength as it goes. This stretching shifts the light toward the red end of the spectrum and slows the rate at which signals emerge from the falling astronaut's perspective. The more extreme the gravitational field, the greater this effect becomes. This isn't just theoretical. Astronomers see versions of this time stretching in the universe. One example comes from stars orbiting close to the supermassive black hole at the center of our galaxy, called Sagittarius A. As these stars pass near the black hole, their light shifts in wavelength in exactly the way predicted by general relativity. These shifts help scientists confirm the mass of the black hole and test how strongly it bends space-time. The slowing of time near a black hole's event horizon also affects the matter that spirals in. When gas and dust fall toward a black hole, they form a swirling disk called an accretion disk. The material heats up as it accelerates, releasing tremendous energy. This makes the regions just outside the event horizon some of the brightest spots in the universe, even though the black hole itself is dark. Light from this hot matter is redshifted as it climbs away from the edge, and the time it takes for this light to reach distant telescopes includes the effects of gravitational time dilation. Observations of these disks give astronomers clues about how fast black holes spin and how much mass they contain. The fact that time slows to a near stop near an event horizon also ties into one of the universe's biggest questions: what happens inside? According to general relativity, once an object crosses the event horizon, it must move toward the singularity at the center, a point of infinite density where the known laws of physics break down. For the infalling astronaut, this journey from horizon to singularity happens in a finite amount of their own time. But no signal can ever escape to share what they see. The event horizon seals off the interior forever from the outside world. This extreme time stretching is not just limited to black holes. It's an extension of the same principle that affects time near any massive object. On Earth, we measure the effect with atomic clocks. In orbit, satellites experience both special relativity and general relativity. Their high speed slows their clocks down slightly, an effect of special relativity, but their distance from Earth's mass means they feel weaker gravity, which speeds their clocks up, an effect of general relativity. Engineers must combine these effects to keep GPS systems accurate. Without accounting for gravitational time dilation, GPS positions would drift by kilometers each day. The closer you get to something incredibly massive, the more dramatic the slowing of time becomes. A neutron star, which is made of the collapsed core of a massive star, is so dense that a single teaspoon of its material would weigh billions of tons on Earth. Time near a neutron star runs noticeably slower than far away. But black holes push this to the limit. The event horizon is where the curvature becomes so extreme that the time dilation factor goes to infinity in the view of a distant observer. This effect also affects light trying to escape. Just outside the event horizon, light can still get away. But the closer it starts to the horizon, the longer it takes to emerge, and the more it is stretched. This is why a black hole's boundary appears so perfectly black. Once something crosses over, its light never comes back out. Even just above the event horizon, light that does escape is red-shifted so strongly that it carries only a ghost of the original signal. Scientists have found indirect ways to test these ideas. The Event Horizon Telescope's image of the black hole in the galaxy M87, released in 2019, shows the glowing ring of material orbiting just outside the event horizon. This bright ring, called the photon sphere, marks where light can orbit the black hole multiple times before escaping. The dark shadow in the middle is not the black hole itself, but the region where light cannot escape. The shape and size of this shadow confirm that general relativity's predictions about how time and space warp near a black hole are right. Gravitational waves, too, carry the signature of extreme time stretching. When two black holes spiral together and merge, they create ripples in space-time that we can detect with observatories like LIGO. These waves show how the final moments before the merger, when the black hole's event horizons nearly touch, are stretched out by time dilation. To the merging black holes, the final collision happens in an instant. To our instruments, the signal carries information about how space and time twist and slow near the horizon. All of this reveals how deeply connected mass, space, and time are. There is no clear boundary between space bending and time stretching. They are part of the same geometry. Near massive objects, both space and time respond to the presence of energy and matter. Black holes are simply nature's way of pushing this principle to the edge of what our equations can handle. These ideas might seem remote from daily life, yet they shape our understanding of the universe. The bending of time near massive objects explains not only what happens near a black hole, but also why the light from distant galaxies can be stretched and delayed when it passes near other massive objects along the way. Gravitational lensing and time delays are essential tools for mapping the hidden matter that makes up so much of the cosmos. In the end, the strange slowing of time near the edge of a black hole reminds us that time is not an absolute universal flow that ticks the same for everyone, everywhere. Instead, it's flexible, stretching or compressing in response to gravity's pull. A clock on your wrist, a heartbeat, the lifespan of a star. All of these follow the same rule. The deeper you go into a gravity well, the slower time runs compared to someone watching from a safer distance. It's humbling to think that while you could, in theory, hover just outside an event horizon and experience time passing normally for yourself, the rest of the universe would speed ahead. You could see distant stars aging, galaxies evolving, and the cosmos unfolding on timescales your own clock could never match. In this extreme slowing of time, black holes show us one of the deepest truths of general relativity, that space and time are not fixed backdrops for the universe's events, but a dynamic fabric that responds to every mass, every burst of energy, and every gravitational well, stretching, curving, and, near a black hole's edge, nearly standing still. If you've ever used your phone to navigate through an unfamiliar city, to find a new cafe, or to track a delivery moving across town, you've benefited from one of the most practical consequences of Einstein's theories of relativity. It might feel like these ideas, curved space-time, the speed of light as an ultimate limit, clocks ticking differently in orbit, should belong only to distant stars and black holes. Yet, hidden behind the smooth blue dot on your map or the voice guiding you down the next street, there's a constant, quiet dance of special and general relativity at work. Without it, something as ordinary as a navigation app simply wouldn't function the way you expect. At the heart of this everyday marvel is the Global Positioning System, or GPS. It's easy to take for granted. Tap a destination into your phone, and your location appears with remarkable accuracy. But underneath this simple interaction lies a network of at least 24 satellites orbiting Earth, each carrying some of the most precise atomic clocks humans have ever built. These satellites orbit about 2,200 kilometers above the surface, moving at speeds of around 14,000 kilometers per hour as they circle Earth twice a day. Their constant, reliable signals provide the timing pulses your phone uses to triangulate its position. For GPS to work, each satellite broadcasts not only its current location, but also the exact time the signal was sent. Your receiver compares the time it receives the signal with the time it was sent, calculating how long the signal took to reach you. Multiply that travel time by the speed of light, and you know how far away the satellite is. By comparing signals from at least 4 satellites, your device can pinpoint your position anywhere on Earth within meters, sometimes even centimeters with special equipment. The surprising part is that these calculations rely on time being measured so precisely that even the smallest drift matters. Here's where relativity comes in. The satellite's high speeds mean they're experiencing special relativistic time dilation. Their motion slows their onboard clocks by about 7 microseconds per day compared to clocks on Earth. That's because, according to special relativity, when you move at high speeds relative to something else, your clock ticks a little more slowly from the perspective of a stationary observer. But there's another effect to account for. General relativity predicts that because the satellites are farther from Earth's mass, they're higher in the gravitational field. Being higher up means they feel less gravitational pull than we do on the ground. This weaker gravity speeds up the passage of time on the satellites by about 45 microseconds per day compared to clocks on Earth. So, the two effects push in opposite directions. Special relativity slows the satellite clocks down. General relativity speeds them up. The result is that the clocks tick faster overall by about 38 microseconds each day. That tiny daily gain might sound insignificant, but light travels about 300,000 kilometers every second, so an error of even a microsecond translates to a position error of about 300 meters. Add up 38 microseconds per day, and your GPS would be off by several kilometers after just 24 hours, enough to make your phone think you're in the wrong neighborhood, the wrong city, or even in the ocean. Engineers build this correction into the satellites from the start, making sure that the time signals account for the stretching and slowing of time predicted by both parts of relativity. Without this, the GPS system would drift quickly into uselessness. This example shows just how practical Einstein's theories are. When he first wrote down his ideas in 1905 and 1915, they seemed almost philosophical. Insights about the deep structure of the universe, beautiful but abstract. Yet today, they shape the accuracy of navigation systems relied on by billions of people. Pilots use GPS to guide planes safely through busy skies. Farmers use it to steer tractors along perfectly straight rows. Emergency services depend on it to find people who call for help. Cargo ships crossing oceans, delivery trucks in cities, hikers in remote forests. All of them rely on this blend of cutting-edge physics and everyday technology. Relativity's influence shows up in other subtle ways too. When we send probes to other planets, scientists must calculate their paths using equations that include the bending of space-time by the Sun and other bodies. Spacecraft, like the Voyager probes, still traveling through the outer reaches of our solar system, navigate with signals that must account for how gravity bends the light paths and stretches the time the signals take to reach Earth. Tiny shifts in timing can add up to big changes in where a spacecraft ends up millions of kilometers away. Closer to home, particle accelerators use special relativity every time they push particles to speeds approaching the speed of light. Engineers know they must add enormous amounts of energy to make particles move even a tiny bit faster as they near that ultimate limit. Without the insights of relativity, we wouldn't be able to design experiments that probe the smallest pieces of matter or test how the universe behaves under extreme conditions. Even in medical technology, relativity quietly plays a role. In positron emission tomography, PET scans, tiny particles called positrons interact with electrons to create photons that travel at the speed of light. The way these signals are timed and detected relies on an understanding of how light and time interact, the same physics that connects back to Einstein's work. All of this rests on a foundation of precise clocks. The idea that time is not an absolute universal river, but a flexible dimension woven into the shape of space, has changed how we build and synchronize those clocks. Scientists use atomic clocks that can keep time so accurately they lose only about 1 second over millions of years. These clocks help synchronize everything from financial transactions to global communication networks. Every piece of digital infrastructure that depends on exact timing, whether it's streaming video, securing data, or guiding high-frequency trading, works better because we understand how time behaves at different speeds and altitudes. Relativity has also helped scientists confirm other fundamental aspects of how our universe works. When they measure how light from distant galaxies is bent and delayed by massive objects in between, they're seeing the same principles that keep your GPS on track. Gravitational lensing and time delays let astronomers map dark matter, the invisible mass that doesn't emit light but bends space-time, and test how accurately general relativity describes cosmic structures on the largest scales. What's striking is that these big ideas rest on the same rules that govern your simple walk through the city guided by your phone. A few microseconds of time gained or lost each day in orbit turn into the difference between getting to the right doorstep or being miles away. The speed of light has a universal limit. The stretching of time near mass, the slowing of clocks on fast-moving satellites. It all plays out above your head every moment, woven into the quiet hum of invisible signals bouncing between Earth and space. Relativity reminds us that the world is more connected than it appears. Time isn't just a background tick-tock, but something that shifts and bends in response to motion and mass. The satellites above you are not just lumps of metal. They're constant reminders that even the simplest seeming parts of daily life rest on deep truths about how the universe works. It's easy to forget how recent this understanding is in the grand sweep of history. For centuries, people thought of time as absolute, marching forward the same way for everyone, everywhere. Now we know that a clock on a mountaintop runs a little faster than one at sea level, that the heartbeat of an astronaut in orbit ticks just a shade differently than yours on the ground, and that the phone in your pocket depends on both ideas at once just to tell you where you are. Every time you follow that calm blue dot on a map, you're tracing the legacy of a simple but world-changing realization. Time and space are flexible, intertwined, and responsive to the dance of mass, motion, and light. The same insight that explains black holes and the bending of starlight across galaxies guides delivery trucks through traffic and keeps planes safely in the sky. Relativity is not some distant, exotic idea locked away in observatories and particle accelerators. It's built into the smallest details of the digital world, woven through every clock and signal that keeps our connected lives moving. It's a reminder that the universe is far stranger and more beautiful than it looks, and that, even as you drift to sleep, your place in that universe is shaped by invisible curves and stretches in time and space. So, when you close your eyes tonight, think of the satellites circling high overhead, the beams of light carrying signals through curved space-time, and the clocks in orbit quietly adjusting so that your world lines up just right. May these hidden rhythms remind you that you too drift gently through a universe where time bends, space flexes, and everything you do, from your first step outside to your journey through the stars, happens within a fabric more flexible than you ever imagined. Good night.